In this video, we'll be looking at Chapter 11, Section I.2 on Venn diagrams and conditional probability. Let's take a look at a simple Venn diagram where we have two sets, set A and set B. Remember from Chapter 1 that the union of two events is represented with this notation, A union B, and that the intersection of two events is depicted with this notation, A intersection B. Also remember that on a Venn diagram, the union is the green shaded area, right? It's anything that is within the two circles. And the intersection is where the two circles overlap. So where the purple shading is. Also remember that union is another way to say or. So an element can be in either A or B, and that the intersection is another way to say and. So in this case, an element has to be in both A and B. Now from previous work, we know that using an OR statement, right, the probability of A or B occurring is equal to the probability of A occurring plus the probability of B occurring minus the probability of A and B occurring at the same time. Using the notation that we learned in Chapter 1 and that we've just reviewed, we can rewrite this equation so that the probability of the union of A and B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. This equation is the same exact equation that we saw in previous sections. It's this equation, just using different terminology. Let's take a look at that equation again. So the probability of the union of A and B, or A or B occurring, is the probability of A plus the probability of B minus the probability of the intersection of A and B, or the probability of A and B occurring at the same time. Now also remember from previous work that mutually exclusive events are events that prevent each other from occurring at the same time. Right? So in other words, for a mutually exclusive event, A and B, they cannot occur at the same time. So what does that look like on a Venn diagram? So if I have my two circles, A and B, for mutually exclusive events, remember that A and B don't overlap. These are also called disjoint events, which we saw in Chapter 1. So these are mutually exclusive, which means that this section right here, the intersection of A and B, doesn't exist. So for mutually exclusive events, the last part of this equation is equal to 0. And therefore the equation is simplified to just the probability of A plus the probability of B. Again, this is only for mutually exclusive events. If these two circles were to overlap, they would be non-mutually exclusive, and I would have to consider that last term. Now let's take a look at some conditional probability equations. First, we need to know some notation. This notation right here represents that A occurs knowing that B has occurred. And this is often also said as A given B. And again, we've seen this before. And if we can represent a situation using a Venn diagram, it's really easy to pick out what B has occurred is, and then to figure out what A is within the context of B occurring. However, when we have a situation that can't be represented by a Venn diagram, say something that has to be represented with a tree diagram, it gets a little bit trickier. So we have an equation that can help us here, and it is this: the probability that A has occurred or occurs or will occur given that B has occurred is equal to the probability of the intersection of A and B divided by the probability of B alone. Now your book has a nice little proof of this equation using Venn diagrams, although this equation is more useful when we don't have a Venn diagram. And it is as follows. Essentially, we know how to use a Venn diagram, a completed Venn diagram, to find the probability of event A given event B. And from the Venn diagram, it looks like this. Using a little bit of manipulation here, and dividing by A plus B plus C plus D, which is the total number of events or possible outcomes, in both the numerator and the denominator, we can simplify to this expression. And I urge you to take a look at this closely to see why that is. But even if you don't, just know that this equation represents the probability that A will occur given that B has occurred. And like any algebraic expression, we can rearrange this for a number of different forms. Like so, if we wanted to know what the probability of A and B was, we could write it by rearranging the equation, simply multiplying by the probability of B on both sides of the equation. Now let's take a look at a few examples. In this example, we're looking at a library group of 50 readers, and we know that 36 like science fiction, 20 like detective stories, and 12 dislike both. And we're asked to find the probability of certain situations occurring if we select one reader at random. In this case, it would be very helpful to draw a Venn diagram, so I'm going to set up a blank one here. So we know we have 50 readers, and we know 36 like science fiction, so that would be this circle, and 20 like detective stories, that would be this circle, and 12 dislike both, so we're going to have 12 people on the outside. So remember, we need to find the intersection first here, and we do that by adding the 36 that like science fiction and the 20 that like detective stories, and we get 56 people. Now that's obviously too many because we only have 50 readers, and this 56 represents, or should represent, all of the people within the circles. But we know that the number of people within the circles is equal to 50 minus 12, which is 38. I can only have 38 people within the circles. So the difference between these two numbers is my intersection. And so that's 18. So we see that 18 people like both science fiction and detective stories. From that, I can subtract 18 from 36 to get the number of people that like only science fiction. And again, I'll get 18. Then I can subtract 18 from 20, who are the people who like detective stories, and that will give me the people who only like detective stories. And we see that that's 2. And if I quickly add up all these numbers, I should see that I get 50. Now for part A, I'm asked to find the probability that a reader likes science fiction and detective stories. So this is really the intersection of S and D, the people who like both. And we know that there are 18 people who like both, and that there are 50 people total. So 18 divided by 50 simplifies down to 9 out of 25. And that's part A. In part B, we're asked to find the probability that the person likes at least one of science fiction or detective stories. So that's really anybody within the circles, right? These people like science fiction, these people like detective stories, these people like both. So in all cases, they like at least one. And so the probability that a person likes at least one is equal to 38, which is the sum of people inside the circles, divided by 50, and that simplifies to 19 over 25. In part C, we're asked to find the probability that a person likes science fiction given that he or she likes detective stories. So from the Venn diagram, we first need to determine the given part, which is detective stories. Within this circle, I see that there are 20 people that like detective stories. So the notation here is going to be the probability that they like science fiction given that they like detective stories. And 20 is going to be on the denominator because these are the only people I'm considering. Only the ones who like detective stories. And out of those, I see that 18 also like science fiction. So I have 18 over 20, which simplifies to 9 over 10. And in the last question, I'm asked to find the probability that the person dislikes detective stories given that he or she likes science fiction. So the notation here is going to be dislikes detective stories. That's the complement of D, right? If these are all the people that like detective stories, these are all the people that don't, right? Given that they like science fiction, well, these are the people that like science fiction, right? So there are 36 people that like science fiction. Out of those, we want to find those who dislike detective stories. Well, these are the people that dislike detective stories out of those who like science fiction. So that's 18 divided by 36, which equals 1/2. One more example problem here. In this problem, we're given jar A, which contains 2 pink and 5 green tickets. So 7 tickets total. Jar B contains 4 pink and 3 green tickets. Again, 7 tickets total, but a different arrangement. A special die is used with 5 faces that are marked A. So not your normal die. 5 out of the 6 faces are marked A, and the remaining face is marked B. And this die will be used to choose the jar. And once the jar has been chosen, then we will select a ticket from this jar. And we want to determine the probability that the ticket will be pink and that the ticket was chosen from jar B given that it is pink. Now this case we can't really represent with a Venn diagram, so it's best to use a tree diagram here. So the first column will be the jar, and the second will be the ticket. Now we have 2 choices for the jar. We have jar A and we have jar B. And the probability of choosing jar A comes from rolling the die. Remember, 5 faces of the die are marked A. Well, I have 5 out of the 6 faces are marked A, so I have a 5/6 probability of choosing A, which leaves a 1/6 probability of choosing B. Now, if A were chosen, then I could draw a ticket from A, and my choices are pink and green. And I have 2 pink tickets out of 7 for jar A, and 5 green tickets out of 7 for jar B. I'm sorry, let me correct myself there. I have 5 out of 7 green tickets in jar A. In jar B, I can also draw pink and green tickets, but in this case, 4 out of the 7 tickets are pink, and 3 out of the 7 tickets are green. Well, now that I have my tree diagram, I can start answering some of these questions. Right? And I want to find the probability that the jar is pink. I'm sorry, the ticket is pink. So the probability that the ticket is pink. I have 2 pathways that can get me that scenario. If jar A was chosen and I drew a pink ticket, I use this path. And if jar B was chosen, to get a pink ticket, I would need to use that path. So in this case, I'm going to multiply along the branches, and I'm going to add the 2 branches together. Okay, and if I do a little bit of simplification here, I get 10 over 42 plus 4 over 42, which equals 14 over 42, which simplifies to a nice 1/3. So this is the probability that a ticket will be pink. The second question is we're asked to find the probability that the ticket was chosen from jar B, given that it is pink. So it's really important that we set up our notation correctly here. We want the probability that jar B was chosen given that the ticket was pink. Right? It's given that the ticket was pink. Now because we don't have a Venn diagram here, this is hard to just determine from the visualization of the data here. So we need the equation that we learned in one of the previous slides here, and that is the probability that A given B equals the probability of A and B occurring divided by the probability of B occurring by itself. So in this case, I want to find the probability of B and P occurring at the same time and divide that by the probability of P occurring by itself. Well, the probability of B and P occurring at the same time is this branch right here. So I multiply along that branch, I get 1/6 times 4/7. And then I divide by the probability that the ticket was pink. Well, I've already found that in the previous problem. It's simply 1/3. So I can do some simplification here, and I'm going to get 4/42 divided by 1/3. Well, remember, dividing by a fraction is the same thing as multiplying by its reciprocal. So I'm really going to get 12 over 42, which simplifies to 2/7. And this is the probability that the jar chosen was B, given that the ticket was pink. And again, we probably wouldn't have gotten that just by looking at the numbers here, so that's when we need to use this equation.